walk through different spaces when I go following the rainfall runoff chain and look here and there and there, and so what we have done. So, first I introduce to you a complexity state space, which is quite simple. Everything is quite simple actually. Then I walked along the geographical state space and look at rainfall events, extremes, and supply and demand. This is two formulas which I like to look at. And then I continue in the systems analysis, which is looking into the eco-hydrological state space, which is somehow spanned within that framework. And here I try to look at one or two things, namely first the global scale, vegetation, and secondly the change which we can get when we look at surface climates, and then like to attribute these changes to climate-induced internally induced causes, and time permitting I may look at closed lakes, and as you have been working on resilience, I briefly show that as an outlook on resilience and the human dimension and the risk state space, which is the fourth space which I want to present to you. But as I said, I will interrupt in time everywhere, and you can ask questions provided I can answer them. Well, you can ask questions, but I don't know whether I can answer them. So this is the uncertainty. This is a complexity state space. If you're looking here, you see the details of descriptions of the modeling point of view. Here, the number of processes which contribute to that, and the vertical axis is the time integration you need for that system. And generally, the people are looking at low-order models, EBM, energy balance models, simple GCNs just for the atmosphere or just for the ocean or something like that. And then you look at GCNs. This is global circulation models or global climate models. And if you really go into detail, you see these horrendograms where you have a lot of things interacting with one another, and this is the ultimate, the state-of-the-art models which are being used in IPCC studies. My leitmotif here is the minimalist model, toy model, and I will be following that. I'm not talking about GCNs, although we have been working on that, developing types of, well, to my taste, quite elegant models, which are portable. You can adjust them very easily, useful for any computer, and even more so, you have a graphical interface where you can just sit in front of the computer, choose which model you want to use, how many layers, and then run the model, and on the run you can change parameters and see how they change visually. So it's good for parameterization, but I'm not going to talk about that. As I said, my leitmotif here is the minimalist toy model, and then I can already go to the next slide. I come to the next chapter. I go to the geographical state space, and I thought I'd present that here because you are in perhaps much better fit to discuss these things, because this has to do with rainfall events and extremes, and this is a scaling law which I found, or everybody finds in the literature in the 1950s. In the hydrology literature, you see that you have the maximum observed rainfall at a certain duration, and here is the duration in log plot, and here is the intensity of the rainfall, and that roughly follows that law 1.5, and I try to say why that could be the case. And the other formula is even older. This is Schreiber's law, 1904, and this is a formula like that. It is the runoff precipitation exponent of net radiation or potential evaporation by precipitation. Schreiber has found that 1904 empirically, and this is a diagram where you plot that. Budico has used this type of approach frequently. It's called the Budico framework, and everybody uses it, hydrologists in particular. And then I thought, why is the formula as it is? And I try to briefly explain that. Goes back to a biased coin flip approach, which is very easy, and I just show that. And then we go to the next slides, next space. Okay, this is not supposed to be actually for that framework, but you have the local time series. This audience knows everything here, I guess. but maybe some aspects may be a bit different. So this is on Tonga core, you see the time series, you have the amounts, and if you look at the amounts and the spectra, you'll see the spectra something like that. You see in particular here the -2 power law. It just suggests that it could be an AR1 process. It's of course no AR1 process, but this is one say, hand-waving argument. And if you use the events only, yes or no events, and that's why I was interested in what you said yesterday, just use that, then you get the flicker noise on that time series. So that I thought, okay, so there's some intermittency in it. If you have the flicker noise, you have the AR1 process, in quotes. And then you might know that Hanachi used the censored AR1 as a model for rainfall, and that's what we like to apply, or did apply. And so that is what it is. You have the AR1 process, and then if you censor it, you say, you know, only the vertical motion brings the rainfall. So we can, to hand-waving argument, explain that. You cut away what is downward motion, and then we can interpret that as a toy model, a censored AR process, with respect to vertical motion observed at a station, and that is what comes out. You know, you just cut it away. The vertical, we did that for, that is plotted for one station here, Fengcheng. This is, we had some Chinese students, and they like to have Chinese stations. You look at the 850 hectopascal here, and ARI data, and you get this autocorrelation of 0.31. And then we say if the efficiency of the system is very high, say 1, then you come up, as I will show later, with the scaling. So that is what is shown here. This is the diagram I showed in the very beginning, Jennings' original. And if you look at that, what you see is you have 3 scales roughly, because here the top is Cherrapunchi. It's 1 year or 2 years in Cherrapunchi only, which brings that scaling here. And then if you look at the other scaling, it's basically Réunion. So this is a synoptic scale, and this is the long teleconnection scale. And here you find convection anywhere, you know, in the tropics and mid-latitudes or subtropics. That is a shorter time scale. You see the slope somewhere here spanned in various, for various scales, for various dynamical scales. So now let's apply the toy model. So up there, we see, you know, Cherrapunchi line with the 0.5, and then we look at single stations. And if you look at single stations in China, we did that, but you could look anywhere. You see the scaling holds roughly, you know, 0.4 or 0.47, something like that. And it not only holds for the maxima in the different time scales, but it holds for the second maxima, third maxima as well. So let's see how the toy model does. And if you look at the toy model, the truncated toy model, that is the AR which we get from the 850 hectopascal data. If you look at the toy model and then truncated, we get a slope of 0.53 just from that. You know, we just look at the AR. So we thought, okay, that's it, not bad. And then we tested the various autocorrelation coefficients, and if you look at that, roughly for 2 orders of magnitude, we have the slope of 0.5, ranging from, say, the autocorrelation 0.9 to 0.1, and then it spreads a bit. So, first subject is finished, so we are quite happy to say that, truncated AR1 is not half bad, explaining or describing the power law for the maximum rainfall you may observe. So we go to the next one, the nice formula, which is Schreiber's formula. Schreiber's original is that one. I don't know to read it in English, translated to English. This is his formula. This is the interpretation, runoff precipitation. It looks a bit like a mixture of Arrhenius formula or a equation of state. You know, if you are a bit legislatic, this is RHO, this is the density, this is the pressure, and then you have something else, RT. So this is an equation of state. It is not, it is the runoff here, precipitation here and that. So what is the theoretical underpinning for that? So we'd like to look at that and did that, and this is the model which is behind it. So how do we start? We start with an upper world and an underworld, all right? The upper world is the atmosphere, and the underworld is the slow soil underground. We have two time scales. We have a fast time scale in between, because we need a biosphere. And the biosphere has a special way of acting. The biosphere gets the rain, and then you have interception, and it is about the time scale of a day or so. And when you have a day or so, then during that day, once it's raining, it evaporates everything there, as long as the net radiation provides enough support. Okay, so if the rainfall is larger than the net radiation, or potential evaporation, if the rainfall is larger, it can go down to the soil. If the rainfall is smaller, everything evaporates, and what is more than that goes up as sensible heat flux. So if you assume now that the daily water supply is given by an exponential, the rainfall is given by an exponential density, then you can put the threshold where the net radiation is, and rainfall above the net radiation and rainfall below the radiation provide you with a biased coin flip. Okay? The biased coin flip is once you are below, once you have rainfall, which is, this is the number of cases here, once the rainfall is below, as I said, is below, everything evaporates and the rest goes in sensible heat, and the other stuff, everything evaporates up to here and the rest goes into the soil. If you apply that, you have a biased coin flip. That's why the biosphere is a biosphere, and so you should laugh about that, but it's okay now. Right. And that provides you, when you do the computations, with that formula of Fraedrich. This is the way how to just look at that. And now we have three equations there. We have this equation of state, and then we have, if you are in equilibrium, the water balance and the energy balance, and then we have the net radiation, the evapotranspiration, sensible heat, precipitation runoff, and we can do something with it. Namely, look at state spaces. You can form different state spaces from these set of variables, and generally the state spaces are formed by ratios. The flux ratios, important flux ratios, which we will be using is D, dryness ratio. This is net radiation over precipitation. So Budico has introduced that, or aridity index. And then you have the runoff ratio, or excess water, and you have the energy excess. Often you see that one here, evaporation. Soil water ratio is used as that one. You can identify then and try to parameterize either that or the evaporation by this and the burn ratio. Furthermore, remember, this is a stochastic model. You can immediately derive from that system the first and the second moments, because, as I said, it's a biased coin flip, and you can do that. And I'd like to show you first a set of various state spaces, which I tend to, I kind of like. You'll be, in the next slides, we will be looking into that state space and that state space, spanned, as I said before, by the variables of the three equations. This is Budico's first, say, way how to look into the dryness ratio, identifying vegetation with respect to external parameter like the dryness ratio. The vertical axis is the net radiation. And if you look at that, you see that you find various biomes here. You see in that, for D smaller than 1, you see the forests, you see the tundra, and larger than 1, you see the steppe, semi-desert, and desert. And you see that D equals 1 is a separation line, which is very important, because on the one side you see the energy limited being separated from the water limited regimes. That's how Budico looked at that. The second state space I will be looking at later is spanned by energy excess. U equals H over N. H is the sensible heat flux. If you like, this is being lost by the biosphere and not being used by the biosphere as energy. That's why it's excess or waste. And the other one here is the water excess. You know, this is just the water not being used by the biosphere, but it goes out of the system and it serves as, say, morphological formations of the ground. Why I say that? Because I'm not talking about this here. These excesses are wasted, and if you look at maximum entropy productions, you see that this is kind of inefficiency of the system which goes out as energy fluxes, and you may use that for optimization processes. But I'm not so much interested in that one here, because we are using that state space because it's relatively elegant, because we are separating the water here from the energy, whereas the dryness ratio is the combination of both. In that one you see that spanned by these coordinates here, you see the dryness ratios here. You have D larger than 1 and D smaller than 1. So this is the wetter and this is the drier side. This Schreiber formula comes in here. The Schreiber formula is, I'm not quite sure whether this is really the best. It's a nice model. I guess it's the simplest model to describe it, which I have shown you above. But there's another equation which really fills along here. And we are just working on that, because this is the Turk curve. And if you look at the Turk curve, it is probably satisfying the energy, the entropy business optimally, because it's a circle with a radius 1 that gives the Turk curve. Anyhow, this is just an outlook, and we will be looking at the attribution a little bit later. So I have talked enough about the state spaces because time is progressing. Here are other state spaces. Is it? Huh?
It's fine.
No, well, still it's fine, but we will talk about that later in a different form. So, Stevenson used the state space, which is quite interesting. He has sensible heat flux here and latent heat flux here, no flux ratio. And you look at the US, and you see here this line, straight line here, is n equals constant. So, Stevenson, in a way, followed a latitude circle around the US. And then you see here the various biomes. In a way, I like that kind of state space. And here's another state space, which is the horizontal axis is the dryness ratio, and here are various flux ratios. And I show you a lot of flux ratios here: the runoff ratio, excess energy bone ratio. Here's the axis for the bone ratio, soil moisture ratio, evaporation, time permitting. This is just a ratio, not a flux ratio. I may be talking about terminal lakes because I like terminal lakes. And terminal lakes are good climate indicators, and many paleo people like that. And I have a minimal model for the terminal lakes where the size of the terminal lakes just depends on the dryness ratio. And these guys often like that, they have different sizes of lakes. So if I do not come to that, I just mentioned that. And this is also very nice because at D equals 1, the terminal lake's area ratio gets larger than 1, and it should not be larger than 1. Then we have overflow, and that happens where the borderline between water limit to energy limit occurs. So it's not half bad. Okay. Why I put these diagrams here? You can put dynamics into these diagrams. Where the trajectories go in the climate system. And this is not dissimilar to our thermodynamic diagram. You have the energy balance, you have the moisture balance, and you have the equation of state. And then you can identify here the radius at a station, and then you find the potential, pseudo-potential cape, and you define energies, etc. And then you can do some interpretations of very basic dynamics. Likewise, I introduced the other diagrams for that matter. Okay, validations. Maybe I skip the whole validation business because it's too much. You look at validation in three ways. At least I thought we should look at that. Consistency, predictability, sensitivity. If I go to predictability, I just take from the GCMs and from observations, say error data, and the hydrologists do that for watersheds. You have everything observed, but you can leave one out, take say net radiation or the dryness ratio, and see what the runoff says. So you can do that in terms of a prediction that the simpler model predicts the same thing as the big model, given certain input from the big model. Okay, I go through that quickly. This is that. Okay, I'll leave that out, and I go directly to the next subject, namely the analysis in the eco-hydrological state space. Okay, so I look at vegetation first, And then at the attribution and the vegetation, we look at the global case. This is, remember, I have shown that this is Boudico, and here in the area from D 1/3 to D equals 1, he sees forests, etc. And we want to test that, whether the vegetation classes he has is roughly coinciding with that, what NDVI analysis, satellite analysis show. That is what we want to see. So how do we do that? We take area data globally. We have the plot in the vertical here, and the upper one is the net radiation plot, and the lower one is the geographical state space here, and the eco-hydrological state space there. You have the net radiation, and you have the dryness plotted geographically. Now, if you go into the eco-hydrological state space, what do you see? Dryness ratio and net radiation here, and this is the number density of the geography. All right. So a data point there you may find here is a number, and you have many numbers. What you see that you have two peaks of frequency, two peaks in the frequency domain. The vertical axis is the frequency out of the domain here, and this is the distribution. You already see that it looks somehow similar in shape as the Boudico curve. What he put there. It's simple. Now look at the NDVI. We take NDVI, 3 classes. The 3 classes, is that visible here? Not really. Okay, so where are the 3 classes? One, you can't, this is the unfortunately in the PDF. This is dark green. You see the indication of dark green here. Do you see that? No, you need my glasses, huh? Okay.
No, we can see.
We can see that, okay. So this is the dark green straddling the D equals 1 line. So this is actually the forest. You know, if you ask the NDVI people, or look at the papers, you see 0.6 to and larger is forest. In between is a transition region, and the shrub region is somewhere grey. It should be greyish there. So in NDVI space, we see that. So actually what we did is we used the physics and add the vegetation as a tracer, if you like. So we have this combination there. Okay, we are almost coming to the end. What you see is that this is the coefficient. No. The question is, the forests do not coincide with that what Boudico says. Okay, so if we straddle the forests, the largest NDVI, with the largest NDVI, we straddle the D equals 1. We go over there. So, and then why could it be? So we looked at the variability, the coefficient of variability, the year-to-year variability. We could also see season-to-season variability, like season, etc. We looked at that, but it's not so important. And if you look at the variability, we have the lowest variability here. The lowest variability for the dryness ratio. The dryness ratio fluctuates from year to year the least, near D equals 1. And if you look at the variability in terms of, this is the dryness ratio here, and this is the coefficient of variability. You indeed see how that is a minimum, and the consequences are quite simple. We test Boudico's geobotanic zonality. D equals 1 doesn't seem to be a borderline, and the minimum variability in D occurs with maximum of greenness. And I think this is quite a nice coincidence, because the cause and effect is what, maximum greenness seems to damp the variability of the system. On the other way around, the system seems to be prone to go for good vegetation to grow strongly where the variability of the dryness is least. Next step, attribution. We go back to the space I have just introduced. We have the excess energy, we have the excess water here in that space. Here is the dryness ratio equals 1. d equals 1. You can express that simply as a linear function. And we want to attribute change in that diagram. If we attribute change, we have to identify a period 1 and a period 2. The period 1 is chosen from, well, basically the data given, and this is chosen from 1982 to 1993 and 1994 to 2006. And we look at the changes here. Changes can be along p equals 1 axis and perpendicular to that. And let's see how it evolves. Because if you already see two colors here, these colors and these colors, you find that here, external, I call it external and internal. This has to do with changes along this axis and changes along the perpendicular axis. And we can easily see in a couple of seconds why this is the externally induced changes and this is the internal changes if we go along that axis. For that we do a Gedanken experiment. No, a bit later. We do the Gedanken experiment. We have different causes of change. Why we call them external and internal, and that goes back to Thoma and Schilling, 2009, and hydrologists have been using that, one or two, not too many hydrologists have been using that. We have the two balance equations, net radiation equals sensor plus evaporation, latent heat flux, and the precipitation, evaporation plus runoff. And we call that the external forcing, climate forcing, changes the net radiation, the precipitation. There's a little caveat here, because albedo change can also be internal, man-made if you like. People call that also changes due to human activity. And this one gives the partitioning between evaporation and runoff, or sensible heat flux plus latent heat flux, and that changes, or the change of the partitioning is what people say could be man-made, or I prefer to say external and internal. Okay, you can now say why that could be the case with this Gedanken experiment. We say first, look first at the internal changes. So in our diagram we have U, the one axis is the horizontal axis. H over n is 1 minus E over n, and W is 1 minus E over P. Okay, so if we fix N and P, so we say climate is fixed, and we only want to change the internal parts. So du equals dE minus dE over N, and dW equals minus dE over P. So we see that once we have no climate change, means P is fixed, N is fixed, we have the sign change in the same direction. So everything what is along this axis here is internal. The other one is external. I do not go through the experiment there. And that is the cause of this, and this diagram is taken from one of the hydrologists who have been using that. So what do we do with it? We try to test it, and we look into a nice region. The region is, as you can see that, is Tibet, the Tibetan Plateau. The Tibetan Plateau, you see here, you see the three different variables. You see the dryness ratio, you see the excess energy, U, you see the excess water, geographical state space, and here is the eco-hydrological state space. The frequencies are given here. You have a bimodal system, which is quite interesting, separated by the D equals 2 line. This is the separation line of these two maxima. And that is quite interesting. Whether it separates the semi-desert from the steppe areas, and there are further interpretations. The separation between the more higher vegetation and less vegetation areas. Here you see again, we looked at the NDVI contributions. And now let's look at the changes. The changes are given here as arrows. You know, here we have the arrows from the first period to the second period following here for the cases where we have increasing vegetation. That's why it's green. And here it is where we see decreasing vegetation. We have 28 points, and these points we are plotting here are only the significant ones. So the trajectories in that state space, the trajectories stop at d equals 1. We have the system getting from the very dry, getting wetter, and it seems to stop here. Whereas that one here, where we have decreasing vegetation, we have a bulk here and another bulk on the other side. This is what is related to the vegetation. Now, unfortunately, the colors are not as good as it should be. These are the attributions already in there. Let's see whether the other slide is. No, this is the vegetation change. This is the vegetation change. Here is increase and here is decrease. Green is increase, and the other one is the decrease where we find that. So to the attribution. This is a bit complicated, but I'm approaching the end soon. The upper one, we look first at the internal and the external causes. The dark blue is the external causes. External causes of that change we observe. The external causes is the dark blue plotted here, whereas the light blue is that one, and the yellow is a little bit here, but we see mostly dark blue, and light blue. To that one I come a little bit later because this is supposed to be pink. This is the Himalaya area. The light blue is the internal changes. The light blue area here is related to a very large increase by about 500,000 of people in the second part of the period which we analyze. So in that area where we just identify light blue internal due to internal changes, we see that one here. The dark blue is climate-induced, and now we come to the Himalaya, which is pink. The Himalaya is a bit funny because the Himalaya says that it should be man-made, the Himalaya areas, according to our the analysis. However, Himalaya was not so much man-made. What we observe in the Himalaya, and I should go back to the other plot. So I show the other plot here. We have an increase in vegetation. And the increase in vegetation does something to the system we are analyzing. An increasing vegetation changes the ground heat flux, because if you have increasing vegetation, that reduces the ground heat flux. But our system did not account for any ground heat flux. Okay? And if that is the case, so that the ground heat flux is reduced from period 1 to period 2, then indeed we find U1 equals n minus G1 and U2 n minus G2. And then you see that the U1 should be larger than the U2, and then the Himalaya should go to become blue. All right? So the conclusion is NDVI greenness helps for interpretation with respect to the attribution of the changes. Another point which I find quite nice is there's fortunately papers, there are a huge number of papers writing about the Tibetan grassland and the net primary production and man-made and not man-made. And this chap here published it shortly before we have published the paper, and we could use that, the area of grassland change attribution. And he said that 65% is due to changing climate with this model, and 30% is due to human activities, okay, for that model. If you look at our data, it's not so much different. You know, if you just look at the 21% of significant changes, not many of the whole, of the 100%, of these we find in our analysis 70% internal and 70% external, 68, and 30% internal. And here we see the differences in decreasing NDVI. But that is kind of, you know, this is a big system here, which he is using, and this is a very easy kind of ansatz which we are following here. Okay, the paper underneath is being seen there. So, how much time do I have?
Yeah, fine.
5 minutes. 5 minutes, okay. So we switched the legs and we switched to GCM where we looked at the globe. 10 years ago we made an experiment. We had looked at the globe as a fully forest covered, and the one system is, and the other system is a parking lot, and see what the differences is in dynamics, and that is quite interesting, the differences. You would not expect it, but after you see the results, then you see, that is why. Okay, now to the human dimension, just 2 slides as an outlook. We can talk about that later if you like. Last century I was a member of the German Advisory Council on Global Change, and the German Advisory Council on Global Change, not on German change, and not on Europe change, all right? So we had to write a report every year, and these are the people who wrote the report, and this is the report of the year 1998. This is a report standing on its own, and this is very well supported by the German government, because we had to hand over that one to the German Parliament. Not that everybody reads it, but we had accompanied by the ministries, and that was 5 or 6, 7 ministries. The experts there attended occasionally the meeting. They tried to influence, but we were kept independent, And then this thing was handed over to the minister and the chancellor, and blah, blah, blah. So, anyhow, and we could enjoy the subject ourselves. We selected the subject ourselves. Every year we did that. Now it's a bit, they just write two reports in 4 years. So this one is the subject, world and transition is everything, strategies for managing global environmental risks. And that is when I learned first time what a risk is. We had a risk expert there, by the way. All these people, this is a forest, this is an economist, this is a lawyer, she is now in the OIGU, psychologist, I don't know what she was. He is a sociologist, he is a physicist, he is a limnologist, Felsinger, economy, and Schulze is a biologist, biochemist.
What do you wrote? Zimmerman?
Huh? The one? Clever.
No, on the last slide. There is a guy.
Zimmerman. 3 economists, they were.
So many.
Yeah. They were quite powerful. Okay. Anyhow, so I realized what risk was, and it took me some time. But the risk state space I'm used to think of is horizontal axis, and the police does the same, of course, is the damage, and the vertical axis is the probability of occurrence. All right? And then you classify, it's unfortunately not, I should have looked at the bad colors. You have 3 areas. You have the normal area, which goes along here. You can't see it, I'm sorry. I should have used the PPT. And here is the transition area, and here is the dangerous area. All right? So at any point here gives you then the classification of risk. The damage the risk does, and the probability of its occurrence. For classifying clusters, risk clusters, we looked at the errors in estimating that, the error in the vertical axis, and we looked at the errors in the damage in the horizontal axis. And if you classify global risks, we have a large number of global risks, we come to clusters which roughly look like that. They have certain different shapes. And we gave these shapes different names. Medusa is, for instance, something which is in that branch you can easily deal with. The medusa is something you hear that electromagnetic wave is disturbing. All right, so people think that is exciting, and it could be a risk, but in reality it's not a risk. You estimate that. Cyclones is something where the damage is relatively high, but the estimate of how the probability is. Cyclops is a guy who only has one eye, and then he just hits. And Damocles is something, you know, it's a very high risk, you know, you have a sword on top of you. You can estimate the probability probably quite well, and okay. Anyhow, and Cassandra is you know, Cassandra is a seeress who is you know, she said that may be happening, nobody is believing her. You know, like with climate change 10 years ago, you know, some people were saying climate change, nobody is believing them, and then maybe very large. All right, so now how does dynamics come in? So this is the risk clusters, because the aim was policy advice. So in policy advice, you do that with changing the motion of your cluster. And here is the Cassandra. You see slightly here that you want what you want to do. Once you have identified that, you want to do to push the cluster into the normal area. That is the policy advice. And strangely enough, for these various clusters, there's almost always the same way of advising. You know, if you have a high uncertainty in the vertical axis for the probability, you have to support research to get more information. If you have a high, if you're very high up here, where the damage is very large, you have to support technology to get protection or something like that. So you find various ways how to reduce that, and in a way this is, you know, the path to resilience is that way, how you put the trajectories in that space, and by that this path to resilience is that you get from the risk cluster classification to say risk reduction policy, and that is, for my taste, what I think would be worthwhile to look at. A brief summary. The walks along the rainfall runoff chain, starting to look at the complexity state space, and I put only the simplest model available because I enjoy that, and then looking into the geographical state space, and that is providing a kind of simple analysis for the Jennings scaling law in terms of a truncated or censored AR1, and the supply and demand side of the rainfall runoff chain provided by Schreiber's equation of state, if you like, in terms of a biased coin flip, and now I understand why the biosphere is wrongly spelled. And then the systems analysis, I was looking at traces. I added to our eco-hydrological state space the vegetation. You can add other variables to that. And then I looked at change or trajectories in the third pole and tried to identify the attribution. Now we are looking, oh no, it's already finished with the Amazon. This is also quite interesting. And I lost out of the Qinghai, Chad, Titicaca, and Lake Eyre analyses of lakes. And the last point, you know, the risk and resilience environment. Thank you very much.
Question? I was expecting a question from you about before the last graph. No.
I'm too busy with the camera. So.
Sorry, about resilience. Don't.
Klaus? You skipped over the bit, it was probably most interesting, right? The validation part.
Oh, okay. Okay.
This is probably the most interesting part, right? Because you showed your model and you showed the truncated AR.
Yeah. Want to see it?
L1 model gives some kind of a power law which resembles the data, but then there was no real validation. Because you say that you know your first and second order moments, and that's really where you get to validate the data by comparing first and second order moments with the rainfall data.
Okay, if you look at the first build, we look at era data and the GCM, and look at the dryness ratio. And if you look at we plot here the dryness ratio and the excess water in the vertical running over precipitation. And the yellow line here is the equation of state. Okay? And the observations here, this is the one, and the other one is era, the other one is the Ekam model. You see the distribution roughly following that line. This is the first moment. I didn't see it here, but before I go to that one, this is the predictability kind of validation. We take the runoff as P minus E, and this is from the GCM, so this is this axis, and we take N and P from the GCM and compute the runoff star from that equation, and that follows that line.
You're validating your model with a model, right?
And error data. Yes, I validate within a given system which is completely comes from a different environment. Oh, why I do that with in that case, is it error? I guess no, it's Ekam, because it's a consistent data set.
So the GCSM is not a data set, right? It's a model.
Data is data. Okay, simulated data and observed data.